we went to chapter 4 where we implemented processor. That was good, so you know everything about the processor. But in chapter 3 in the book, we were talking about arithmetic, how arithmetic is done in the computer. Of course, we have add, subtract, multiplication, division. We talked about integer mainly, but we also have floating points which need to be considered in the computer. In the computer, of course, we do have floating operations. So this chapter talks about these things. About in chapter 2, in chapter 4, we talked about instruction set, and we built a data path, then added controls to that, and then talked about pipelining. In chapter 3, we are going to talk about operations on integers, then about addition. Operations on integers would be addition and subtraction, multiplication and division. We will talk about these 4 operations in that. And we should talk about overflow that you could see later. Then we will talk about floating point. Floating point real numbers like 1.25. These are floating point numbers. How do we represent them? In integer, you know that, how to represent them. In binary, 5 becomes 1, 0, 1. How to represent floating point numbers with in binary. So binary add, it's very simple. You know in your courses, if not in the higher school, in the university, ITI 1100, we do it as we do in decimal. So in decimal, you know, for example, 5, 3, 7, 4 plus 6, 8, 9, 1. We are adding these two together. 4 plus, we start from the least significant digits from the right. 4 plus 1 becomes 5. 9 plus 7 becomes 16, so we have 6. And then we have a carry over to the next digit, which is 1. We have 1 plus 3, 4, 4 plus 8, 12. 2 is here, and 1 carry goes to the next digit. Then we have 1 plus 5, 6 plus 6, 12. And 1 goes to the next digit, and there is nothing, so it is 1. This is how we do it in decimal. So in binary, it is easier because we only have two numbers, 0 and 1. Here we have 10 numbers, 0 to 9. So it's easier. 1 plus 1 becomes 10 in binary. Becomes 10, so we have 0 and 1 coming here, 1 carry. 1 plus 0 is 1. 1 plus 1, again, it is 0, and we have 1 coming as carry. 1 plus 0 plus 1, again, becomes 0, and we have 1 here. 1 plus 1, again, 0, and we have carry here. 1 plus 1 plus 1 is 11, 1, 1. So we have 1 here and carry here. 1 plus 0 is 1, and 1 plus 0 is 1. Exactly the same as we did in the decimal, even it is simpler because it is only two values, 0 and 1. So this is how we did it. There is carry? No carry. Why is that? No, there was no carry. So it should be 0. So there was no carry. If there was something, for example, if I had 1 here, then the last digit becomes 0 and we have carry here. So it means when you add 2, here it is unsigned, 2 unsigned numbers together, how many bits they are? 1, 2, 3, 4, 5, 6, 7, 8. 2 8-bit numbers together, the result could be larger than 8 bits. It could be 9 bits, as you could see here, for example, if we had. So at that time, we say that we have overflow because we are in 8-bit operation. Two 8-bit numbers added together, and we have to put it in 8-bit register, but it doesn't fit. So we have overflow. We have to think about overflow more in the following slides. How do we do this in binary? As you could see in a binary, for example, 1 plus 1 is 0, and then we have a carry here. So in binary, if you look at each slice independently, which they are all similar. If you look at one slice, let me circle one slide. This is one slide. So we add these three together, and then the result would be again a sum and a carry. So if you look at each slide, and it is repeated everywhere. So again here, we have three values added together, we get a result and a carry. Again, three values added together, we get a result and a carry. So if you look at there, we have this, which is repeated. We have a bit from, let's say, number A, this is A, this is B. We have a bit from number B, and we have a carry coming from the previous stage to this. We have a carry in from the previous state. We add them together, we get a sum for this bit, and then we also may have a carry for the next stage. So as you could see, this is the full adder circuit. It gets three inputs, a carry from the previous stage plus 2 bits from two values, two numbers. Then it produces the sum and the carry. The sum of this bit plus the carry goes to the next bit. Okay? This is the full adder. So if we repeat this, then we will have the adder circuit. If I put 1, 2, 3, 4, 5, 6, 7, 8 of this for this design, then I have a full adder. And for the first stage, I don't have carry coming from previous stage. I put 0 for the first one, but I repeat it. So the first one gets CI as 0, but the next stage gets its CI from the previous stage. Okay? And the last carry, CI plus 1, C out, indicates the overflow. Is there a carry? Is there an overflow or not? Another example. This time, okay, it's unsigned, it's still unsigned, so the same thing says overflow if result of out of range. Okay. Now let's think about signed. Since we are adding 7 plus 6 and they are both positive, it is still the same as before because the sign bit, which is the most significant bit, is 0 for the positive values. So it's the same as what we have talked before. But what if there was overflow? Let's do it. You remember in signed values, for example, if we have 8-bit signed values, what was the range of the numbers? It comes from minus 128 to plus 127. Remember? 8-bit signed numbers, they are from minus 128 to plus 127. So let's have two positive numbers added together. Something big, for example, 100 plus 90. 100 plus 90. 100 is, let's make it easier. And 96 is 64 plus 32. So this is 96. This is 96. 64 plus 32 plus 000. This is 96 in digital. And added to, for example, 48. 48. 48 is 32 plus 16. Let's add them together. 0, 0, 0, 0, 0, and 1, 1, 1, and 1, 0. Then this 1 coming out, 1 plus 1, 0. There is 1 here, 1. Now look at this number. That's the result. We are talking about signed operation. So if you look at this number, the result, what is this? Is it a positive number or negative number? No. How could you say it is negative or positive? Look at the sign bit. Positive or negative? Negative. The sign bit is 1. So it is a negative number. How come? We added 2 positive numbers together and the result was negative. It means that we had overflow. We could expect that from the beginning because when you add 96 plus 48, it is more than 127. It is out of range. And for sure, it has overflow. And you see that. It's overflow. Okay? Yeah? So we have to be careful. Let's say about a 2 minus value. For example, something that when you add them, it goes less than minus 128. For example, let's do this, minus 96 plus minus 48. Minus 96. What is minus 96? You 2's complement that. To do 2's complement, you have to go to the first one, and then from that you complement. So minus 96 would be this. Let me put it in blue. Minus 96 would be 0, 0, 0. I hope you know how to do 2's complement. 0, 1, and from this one we complement. 0, 1. This is minus 96. This is minus 96. Let's write minus 48. Minus 48 would be 0, 0, 0, 0. This 1. And then from here you should complement 0, 1, 1. 1, 1. This is minus 48. The first one is minus 96. This is the minus 48. Let's add them together. 0 and 0 is 0. 0 and 0 is 0, 0, 0, 0 and 1, 1, 1 and 0, 1, 0 and 1, 1, 1 and 1, 0 with overflow, with carry, not overflow, sorry, with carry. Look at this number, 0, 1, 1, 0, 0, 0, 0. Is it a positive number or negative number? Sign bit. Sign bit is 0, so it's positive number. Again, you see, we have added 2 negative numbers and the result became positive. So it means that we had overflow and the result is not correct. You should disregard the result. It is not acceptable and something happened. For example, what you should do to solve this problem, you should make your system bigger. You started with 8 bits, so start with 16 bits, or start with 9 bits at least. If we add 9 bits, then plus 96 would represent this, plus 48 represent this, and then when we add them together, we get this. So this is a positive number, which is the sum of the 96 and 48. And for the negative also, if we had 9 bits, this is minus 96, this is minus 48, and then if you add them together, 1 plus 1 is 0, 1 is coming here, 1 plus 1 plus 1 is 1, and we had a 1 coming out of this. The result is negative, and it's correct. You added minus 96 to minus 48, and you got this result, which is correct. But it is 9 bits. 8 bits didn't fit in 8 bits, of course, because the result is less than minus 128. With 8 bit, you could have up to minus 128, not less than that. So this is the thing. So overflow is important when you are especially when you are in signed operation. In unsigned operation is also important, but in unsigned operation, it is easy. When you have overflow, then you know that there is a carry that you could add 2 to the power of n to that number, and then you get the correct result. But here, what could you do with this number to make it correct, a positive number? And how could you do that for this one? So it is complicated. It is actually wrong. This is a wrong result. So we have to be careful about the overflow in especially signed operations. Okay, so let's read in the slide. It says, overflow if result is out of range. Adding a positive and a negative operands, there should never happen an overflow. You add, let's say, a very big number. The maximum number positive would be 127. Let's say we are 8 bits. Then you add it to a negative number, whatever it is. Do you want me to add to the most smallest negative number? It is minus 128. So the result would be minus 1, which is good, which fits in 8-bit. And even if you add it to minus 1, the smallest one, 127 plus minus 1 is 126. So there is no problem. So it means if you have a positive value and a negative value, then you add them, there is never an overflow, for sure, no overflow. The result would fit in 8 bits, for sure. But when we have 2 positive numbers added together and the result is negative, we added 2 positive numbers, the result is negative, it means that there is overflow. And if we added 2 negative numbers and the result would be positive, it means that an overflow happens. So we have to take care of these things. Okay? So overflow should be something that we should take care of that. Subtraction. We talked about addition. Subtraction is almost the same as two's complement mechanism. We invented two's complement because of this. Because with two's complement, instead of subtraction, you could do addition, but adding to the two's complement of the second number. If you want to have A, for example, let's say 9 is another. Let me put 4 bits so it's easier. Let's say, for example, we have 0, 1, 1, 0 minus 0, 1, 0, 1. What are they? The first one is 6 in decimal. The second one is 5. 6 minus 5. The result should be 1. Let's do it. In just doing subtraction, you could do that, but we don't do that. We don't do that in hardware. We use addition. But if we want to do it, yes, let's do it. 1 from 0, it doesn't work, so we have to get 1 from here. So this becomes 0, this becomes, this becomes 10. 1 from 10 is 1. Now we have 0 from 0 is 0. We have 1 from 1 is 0. We have 0 from 0 is 0. So it becomes 1. Yeah. So 6 minus 5, we did it. But it is not the way that we do in hardware. In hardware, we make the second one, the two's complement of the second one, and then add to that. So we had 6 and we had 5. The two's complement of 5. As I told you, you start from here. The first one, you put it there, and then you complement the next. So 0 becomes 1, 1 becomes 0, 0 becomes 1. This is minus 5. This is minus 5. And this is plus 6. We add them together now. 1 plus 0 is 1. 1 plus 1 is 0. Then we have a carry. 1 plus 1 plus 0 is 0. We have a carry. 1 plus 1 is 0, and we have a carry. So look at the result. It is 1. It's okay. 6 minus 5 is 1. And everything is good. So when you want to do the subtraction, then it works with addition, but the second number should be 2's complemented, should be negated, should be in decimal, we just put minus there. It's like that, but we do it in 2's complement representation. The same thing that we talked about overflow in the addition, we can say here. If you are subtracting a positive number with a negative number, then you might get overflow, because positive minus negative, it is like addition of two positive numbers. So there might be overflow. If you subtract a negative number with a positive number, again, a negative number minus a positive number, it is addition of two negative numbers, so we might get overflow. But if you subtract a positive number from a positive number, so never overflow happens. If you subtract a negative number from a negative number, so you never get overflow. Again, the same thing that we talked about in addition, in subtraction, but it is the negation of that. Example, 7 minus 6 is 7 plus minus 6. And minus 6 will be represented in 2's complement. 6 is this, 4, 2, this is 6. When you want to 2's complemented, for example, in 32 bits, here is 32 bits. Let's say it's 32 bits. So starting from the right, 0 is there, 1, the first one is there. You know, the thing is that you complement every bit and then add 1 to that. You know that, yeah? But to do it fast, this is the way that I am saying you. You start from the right until the first one and then negate everything. It is the same as converting, inverting, and adding 1. Inverting every bit and then adding 1. So 0, 1, 0, and the other zeros that we have here, they are all became 1. So this is minus 6 here. So 7 plus minus 6, when you add them, you get 1. That's good. 7 minus 6 is 1. Overflow if result out of range. Subtracting 2 positive or 2 negative value never produces overflow. Subtracting a positive from a negative, we expect that the result should be positive. A positive number minus a negative number, the result should be positive, but you might get negative. If you got negative, it means that there was an overflow there. If you got positive, that's okay. Sometimes you, for example, you subtracting 7 minus 8 for 8-bit numbers. 7 minus 8 is 15, and it is not out of range in 8-bit numbers, so it's okay. But it might get out of range when the result is negative, when you are subtracting positive minus. Okay, subtracting this from this, it should be, I don't know. This is the positive value minus the negative value, or the minus value minus positive value. Which is that? When we are saying subtracting this from this, how do we write it? This.
The negative minus the positive.
The negative minus, because we are subtracting this from that. Okay, so the result should be negative here. The result should be negative. If it is positive, it means overflow. Overflow, if result, yes, the result should be negative, and if the result sign is positive, then it means overflow. So you are right. That's what I thought, because when you are subtracting something from that, so it is at the top, and the second one, it does it. Subtracting negative from positive, positive minus negative. So it should be positive. If the result is negative, it means that there is overflow. Okay? So let's use our adder that we have built before for also subtraction. So let's start with adder, then we go to the subtractor. So adder, as I told you, we have a very simple circuit accepting three inputs, AI, BI, and CI, and generating two outputs, SI and CI plus 1 or CO, carry out. So we use this 8 times, and then we get the result. So this is the result of one of them, because you see, when we have AI, BI, CI, we have CO and SI. The truth table is this. When all of them are 0, the result is 0. When there is 1, 1 here, then the result, the sum is 1, the carry is 0. When there is 1, 1, again, the result is 1, carry. When there is 2, 1, then the sum is 0, the carry is 1. When there is 1, 1, again, 1, 0, 1. When there is 2, 1, again 1, 0. When there is 2, 1, 1, 0. When there is 3, 1, the sum is 1, the carry is 1. So this is the truth table. So we will put the Karnaugh map for each of them separately. This is the Karnaugh map of S, sum, and this is the Karnaugh map of carryouts. You remember Karnaugh map? How do we do that? But this is very simple. We don't need to put the Karnaugh map. So this is very simple. It is sum is 1 when there is 2 ones. When there is 1, 1 or 3 ones. Okay, 1 or 3 ones. When we have 1, 1 or 3 ones, then the sum is 1. So we just use, what do we use? The odd calculation. How do we calculate the odd parity? Did you have it before? We can use an XOR. XOR is very good. When both of them are 1 or both of them are 0, then the result is 0. When one of them is 1. So we just use an odd parity. I show you the circuit. But for the carry, when at least we have 2, 1, either 2 ones or 3 ones, then we have carry. If we have only 1, 1, or we don't have any 1, then it is 0. You see? 0, 0, 0, 0. But here 1, because we had 2 ones. So it is just calculating the voting mechanism. If we have 2 or more ones, we can use AND for that. It's very simple. Let me show you the circuit. So this is the parity. We use XOR, AI, BI goes there, and then the result goes with XOR with CI. So this is SI. And for carry out, we use majority calculation. If A and B, both of them are 1, then we have 1. If, for example, they are not both 1, but CI is 1 and B is 1, 2 of them should be 1. So if 2 of them are 1, the result is 1. So this is the circuit for carryout, okay? But this was just 1 bit. 1 bit, adding AI, BI, CI, and we get SI and CI plus 1, which I called it CO here, carry out. So we can build this. Okay, you can just change something here and using this, so you could get a less gate circuit with two ANDs, 2 XOR, 2 ANDs, and 1 OR. So this is the full adder circuit. If you look at here, there is another adder without CI. If you don't have CI at the first stage, for example, you don't have CI, then you could use a half adder. Half adder means just calculating AI plus BI and then generating only SI and even not the carry. So this is a half adder. sometimes we use them. I will show you an example for using a half adder. So this is half adder, this is full adder. I hope that you have seen that in the previous course. Otherwise, now we have this, then we can connect them together and it works. You see, A0 and B0 plus the first carry, which is 0 because we didn't have the previous bit. So it generates S0 and generates a carry which goes toward the next stage. Then we have A1, B1 with this. Again, S1 is generated here and carry coming here. A2, B2, and so on. Okay? We call this a ripple carry adder, and it is the slowest implementation of an adder. We have another implementation, another way of implementing adder, which we don't go through that in our course. You get it in another course, which will be faster. We do something in parallel, because here you have to wait. There is a delay until this C1 is generated. Then until this is going to be generated, this cannot function. It should wait for C1 to come and then calculate C2 and S1. And this C2 should be generated, then the A2, B2, the full adder number 2 should work. And then C3 should come, then full adder number 3 works. So it is very slow. It is ripple carry. The carry ripples through, and it has slow performance. But it's good. It's a very simple design. When you don't need a very fast adder, then you can use this. For example, if you want to have an incrementer, just adding 1, then you can use half adder. Half adder is good for this one. So if you just use a half adder and put 1 instead of A0, so A0, B0, we have B0 and 1. So this is the result. And the carry from here goes, the carry from here goes to, again, A1, because half adder doesn't have carry in input. So it goes to A1, so we have an incrementer. Okay. Subtractor. Subtractor told you, A minus B is the same as A plus minus B, and minus B is 2's complement, which is the invert of B plus 1, A plus B complemented, B bar or B prime plus 1. So how do we implement? We implement this. We very easily implement B naught. B naught is just using NOT gates for every bit and then adding a 1 to that. So if we use the first carry as 1, because in our adder, the first carry was 0, because there was no carry from the previous stage. But for our subtractor, all of the bits of B are inverted, and then for the first stage, we also put a carry of 1, so we have the 2's complement of B. So we have implemented a subtractor. You see, this is adder, the same circuit as adder, but we got B, we inverted B, and then we put 1 for carry. So this is A plus B bar plus 1, which is A plus minus B, which is A minus B. So this circuit is calculating the subtraction, A minus B, very easily. Yes? Using adder. Using an adder, you could build a subtractor very simply. Okay. Now that we have adder for subtractor, why don't we have a general circuit for adding and subtracting and having one control signal to say it is add or subtract? Okay? So we use a signal called add subtract. When I put bar at one of them, it means that if it is low, it is add. If it is high, it is sub. You know the representation. When you put something like that, add, sub, add bar, then it means this control signal, when it is 0, it is add, because add had some bar. When it is 1, then it is subtract. For example, if you put, let's say, read, write, if you have a signal like this, then this signal means if you put 0 for that, you are doing write. If you put 1 for that, you are doing read. So this is the representation. So we use a control signal called add bar / sub, and then we use it for calculating either addition or subtraction. This works. Look, if it is 0, if it is 0, it means add. I told you it is add. So this 0 comes here. So the carry in is 0. The add should start with carry in 0. And this 0 goes to these XOR circuits. You know, 0 XOR something means that thing, doesn't change. So B3 coming here, B2 coming here, B1 coming here, B0 coming here, and carry is 0, so we are adding A to B. That's adder. Now let's say that the control signal is 1. Now the control signal is 1. When it is 1, it means sub. From this representation, it's sum. So if it is 1, then it means that one pin, one input of XOR are 1. And you know, 1 XOR anything would be not of that. 1 XOR anything would be invert of that. So B3 bar coming here, B2 bar coming here, B1 bar coming here, B0 bar coming here, and this is 1, so we have 1 coming here. So this is a subtractor. We are adding A plus B bar plus 1, which is a subtractor. So we have built a very good circuit, a configurable adder subtractor. If you put 0, it adds. If you put 1, it subtracts. Very good. We talked about overflows. So we told you if positive plus positive is negative means overflow. If negative plus negative becomes positive, it means overflow. So positive plus negative never generates overflow. Negative plus positive never generates overflow. In sign subtraction, positive minus negative should be negative, positive minus negative. If it becomes negative, it means overflow. It should be positive. If it becomes negative, it is overflow. If you do negative minus positive, it should be negative. But if it becomes positive, it means overflow. And positive minus positive or negative minus negative never generates an overflow. So how do we find when we have overflow? It should be simple. You just need to look at the sign bits to see if the sign bits, for example, you are adding A plus B with 8 bits. If A7, which is the sign bit of A, is 0, B7 is also 0, and then S7 is 1, so it means overflow happened because you are adding 2 positive numbers and you are getting a negative number. Or you could see if A7 is 1, which means negative number. B7 is 1, which is negative number. But the result S7 is 0, then it means overflow. If we look at the inside the adder, full adder, C0 C0 coming first, and then C1 goes to the next stage, and from here C2 goes to the next, C3, C4, and so on. If we look at that, then let's look at the last stage. Let's say at the last stage, which the bit is the sign bits. So if in the last stage, the sign of A and B are positive, and we have a carry-in of 0, if they are 0, and the carry-in is 0, of course, the sum would be 0, the carry-out would be 0, and it means that two positive numbers have added and generated a positive number, so there is no overflow. So overflow is 0. Look at carefully. If there are two positive numbers, the carry-in comes in, 0, 0, 1. So what would be the result? The sum would be 1, the carry-out would be 0, the carry-out out of the 8, out of the last bit. Here, we have added two positive numbers, and the result is negative. So it means that there is overflow. Okay? Good? Do you follow? Are you following? If A is positive, B is negative, and the carry-in coming in is 0, so 0 plus 1 plus 0 is 1, 0. So again, we have a positive number plus negative number, and the result is negative. So okay, it's negative. It's okay. I told you there is no overflow when you are adding a positive and a negative value. So there is no overflow. Again, if A is positive, B is negative, for sure there is no overflow. If A is negative, B is positive, no overflow. If A is negative, B is positive, regardless of carry-in, there is no overflow, okay? But if A is negative, B is negative, and the carry-in from the previous stage, n minus 2. So n minus 1 is the last stage, n minus 2 coming is 0, then 1 plus 1 becomes 0, and we have a carry out also, 0, 1. Here you see negative plus negative became positive. So it means that there is overflow. There is overflow. And if there are two negative numbers and the last stage has a carry, then when you add them together, you get sum as 1 and carry as 1. So again, sum is negative, two numbers are negative, so there is no overflow. So this is the truth table for overflow. So look at overflow. Overflow is only 1 at this and this. Let me highlight it. So overflow is 1 here and here. So what would be the function of this? If you look at this, this only happens when, okay, let me see. Yes, it only happens when carry in and carry out are not the same. Look at that. When carry in, carry out are both 0, overflow 0. But when carry in is 1, carry out becomes 0, then we have overflow. And here, if carry in is 0 and carry out is 1, then we have overflow. So very simple. Overflow is what? When they are different, it is overflow. What do we use? XOR. XOR is very good. So overflow function is the XOR of carry in and carry out. Very simple. So if you have an adder, a full adder, you just XOR the carry in of the last stage with the carry out of the last stage, and you generate overflow. And we needed this because we should know if overflow happens or not. If overflow happened, it means that we had to do something. The result is not correct. So here is this. Here, the last carry in is this one. The carry out of this one. If you XOR these two together, you get overflow flag. The overflow flag is 1 when there is overflow. The overflow flag is 0 when there is no overflow. And it is very important. If you got overflow, then it means that the result is not valid. Throw it away. If, again, if A and B are signed numbers, sub 0 means S. We did this thing, so let's go on. Okay, C out is addition overflow indicator if we are unsigned numbers. If you are unsigned numbers, then C out is the not of C out is the borrow. If you are adding to unsigned number, the carry out from the last stage is the indication of the overflow, the carry. If you are subtracting two unsigned numbers, then the carry out, if it is 0 from the last stage, that it means that there was no borrow. But if it is 0, then it means borrow. So not of C out is subtraction underflow indicator if we have two unsigned numbers. But for signed numbers, we talked about it before. How do we calculate? Again, I say, if in signed addition or subtraction, we got overflow, output S is invalid. Throw it away. But with unsigned number, you can just add something to that and you get the good result. In some languages like C, they ignore overflow. In MIPS also, in MIPS, we haven't talked about this before. In the instruction sub of MIPS, the unsigned operations of add and subtract, they don't generate overflow. So it is your responsibility. If you would like to care about overflow in unsigned operation of add U, for example, add U, add unsigned immediate, or sub U, sub unsigned, then you have to think about it yourself. But in MIPS, the other operations like add immediate, sub, which they are signed operations, then it checks overflow. And what happens if overflow happened? It generates exception. We didn't talk about exception before. Exception is some kind of a trap. When the processor has an exception, it means that something is wrong. It should go to somewhere else, do something for solving the problem, and then coming back. Exception is that. If the source of exception is external, we call it interrupt. Have you heard of interrupt? No? Okay. If you have microprocessor, you know interrupt. So interrupt, exception, they are almost the same. We don't go through the detail, but you should know that add, sub, and add immediate, which are signed operations, they generate exception in MIPS, and it means that when exception happens, MIPS goes to a place which is already defined. It's not up to us. It's already defined. It goes to that position. It saves the PC, the current PC, which exception happened there. It saves this into a register called EPC, exception program counter. It was not among the 32 registers that we were seeing before. It is another register, exception program counter. It goes there, do whatever it wants, And at the end, we have to come back to where we were when exception happened. And the instruction for getting EPC is MFC0, move from coprocessor register. This is called coprocessor register. So that's it. We don't go further for that. In MIPS, exception is, the overflow is this. Unsigned, nothing, doesn't do anything for unsigned. For signed, it makes exception. So the last slide, I guess, for today would be this. We talked about addition and subtraction. And in MIPS, there are 32 bits. ALU is 32 bits, and that's it. Why I am saying that's it? Because in some processors, even the ALU is, for example, 32 bits, but you can somehow tell ALU to add 2 8 numbers together and the other 2 8 numbers together and doesn't combine the result. So the carry from the first 2 8-bit numbers don't go to the next stage. So you can have separate 8-bit adds or separate 8-bit subtraction. And this is good for multimedia. Why? Graphics and media processing operations, usually they work on 8-bit or 16-bit data. For example, if you have a pixel, a color in a computer, it has usually 3 color value, RGB, red, green, blue. And each of them are 8 bits. Or it might have intensity value, which again is 8-bit. When you want to do some operation on these values, the color, for example, of the pixels, you are adding 8-bit values, not 32 bits values. So the processor, we are wasting the 24 bits of our ALU if we are just adding 2 8-bits value. So it is good if we have a processor who could make different, for example, concurrent 8-bit additions with its ALU. MIPS doesn't do that. We told you, MIPS is very simple, regular, so in MIPS we don't do that. But for example, in x86, in Pentium, we have these kind of instructions that you could add 4 8-bits. Or 16-bit data. For example, in audio, usually when you digitize audio, you get 8-bit values for each sample. 16-bit values for each sample. So again, here you need 16-bit operation, not 32-bit operation. So if you have a 64-bit ALU, or in our MIPS 32-bit adder, then if we could partition the carry chain, so the carry from, for example, this is 4 8-bit numbers. If we use the regular operation, we just add 32 bits together, and the carry from this goes here and adds up. If you could partition the carry chain, so the carry from here come out, the carry from here come out, not going to the next stage, then you could have 4 separate 8-bit additions. So this is something that we see in some processor. And we call these instructions SIMD, single instruction, multiple data. With just one instruction, you write add for your instruction, you write add. But you are doing 4 adds for different data. Single instruction, multiple data, SIMD. So it's a kind of parallelism, making something parallel happens. The other thing that we might need, in addition to whatever we have covered before, is saturating operations. For example, again, in the multimedia, if there is a pixel and you are working with intensity values, and then you would like to make the image brighter. To make the image brighter, you add to the intensity values. But intensity values is 8 bits, from 0 to 255. When it reached 255. If you add 1 to that, it becomes 0. 0 means, the 0 means black, 1 means white, and between that 0 to 255 means white, and from that it's gray levels. So you need some kind of saturating. When you are adding, going up, you are making it brighter, brighter. Then when you reach at the 255, you don't want to become 0. Then it becomes dark, it becomes black. You want to clip there. You want to keep it there, saturate it there. That from 255 still remains 255. 255 plus 1, 255. 255 plus 1, 255. In regular addition, 255 plus 1 is 0. So this is something else that we might need in a computer. Again, MIPS doesn't support this, and it doesn't work that way. So that's it. So we have covered addition and subtraction. Next lecture, hopefully we could do multiplication and maybe division, maybe, hopefully. So let's see what happens. So before going, let's do the attendance. Go to the course. I have to, I guess, update the time. It is 3:52. So the attendance is here. Arithmetic for computers. Attendance. And so ending 3:55. Update. So the password is 030710. 030710.